Hello, in this video we will look at how we can use the Ti-83, Ti-84 graphing calculator to calculate the mean or expected value and standard deviation of a discrete random variable or a discrete probability distribution. Recall that a discrete probability distribution is for numbers that are counted or innumerable or non-infinite rather. So we're looking at countable variables. The formula is to add up all of the x values times their probabilities, or x times p of x. There's another video that you can watch that explains this in a little bit more detail and shows this process, but for today's video we are going to focus only on using the Ti-84. So example 4.5 says, find the expected value of the number of times a newborn baby's crying wakes its mother after midnight. Let the discrete variable represent the probability that a newborn baby's crying wakes its mother after midnight in a given week. We want to find the expected value of the number of times per week a newborn baby's crying wakes its mother after midnight. And then it says calculate the standard deviation of the variable as well. All right, so the x variable represents the number of times the mother is woken up in a week. Ignore my horrible handwriting there. So what we need to do is type in all of these 7 values into L1 in the calculator. To access that, we're going to press stat and then press enter. We have some data values in here. We can clear those data values by pressing up, highlighting the list and hitting clear. And then when we press back down, it'll clear the list. Over, up, clear, down, back. All right, so we got 0, 1, 2, 3, 4, 5, 6, 7. Now with these probabilities, they are all fractions, but we can type those fractions right into our calculator using the division symbol. So 2 divided by 50, 10 divided by 50, 21 divided by 50, missed it, there we go, 9 divided by 50, 3 divided by 50, 2 divided by 50 twice, and then lastly 1 divided by 50. Notice that when we type in those fractions into the lists, the calculator automatically converts these to a decimal. All right, so we have the x values in L1, we have the probability of the x values in L2. Now we just need to calculate them. We will press stat, go to the right to calc. We only have one variable. That variable is number of times the mother is wakened. We are not doing 2 variables, we're only doing 1 variable. So we're going to press enter on 1 variable. Our list is L1. Our frequency list is L2. It's not a frequency, but it's a probability list. And we're going to go down to calculate, and we will get that the mean is 2.4. So the expected number of times that a newborn baby's crying wakes its mother after midnight is 2.4 times per week. Now the interesting thing about this is that, where'd my mu go? The number 2.4 cannot actually happen in this probability or in this experiment. There is no way that a baby can wake its mother 2.4 times in a week. It could wake its mother 2 times in a week or 3 times in a week, but it cannot wake its mother 2.4 times in a week. However, if we were to add up all of these values, if we were to look at the number of times a baby wakes its mother repeatedly for many, 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 many weeks, and then add up all of those values and divide by the number of weeks that we're looking at, we would find an average of 2.4. And that's what this really represents. What would the average be if we were to do this long term, if we were to do this many, many, many times? Again, this is theoretical. It can never actually happen, but it is a projected expected mean. The standard deviation for this example is 1.456 or 1.5. And note that both of these values are population values. There is no sample values here. Since we're talking about this in a theoretical application where we are talking about this repeatedly, this experiment being repeatedly done for many, 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 many times, we're looking at these values as though they are population variables rather than as sample variables. All right, so we have another example that we can work on. This one says, a hospital researcher is interested in the number of times the average post-op patient will ring the nurse during a 12-hour shift. For a random sample of 50 patients, the following information was obtained. What is the expected value for number of times the call bell is pressed? The expected number of times the call bell is pressed. All right, so again, we have a probability distribution where our x values are going to go into L1 in the calculator, and our probability value is going to go into L2 in the calculator. Stat, enter. Now, the nice thing about this example is that we only have to change one column, really. We can get rid of 6 and 7. And now we have the x variables. I'm going to go up, press clear, go back down, and now we've edited the lists. So we have all the x values into L1. We're going to type in the probabilities into L2. Again, fractions just get typed in with division, and the calculator will automatically convert these to decimals. And then we have 14 divided by 50. And then 6 divided by 50, and then 2 divided by 50. All right, so now we have L1 and L2 entered into our calculator. Stat, go to calc. Again, we are only dealing with one variable, that is the number of times the call bell is pressed. Our list, our values are in L1. Our frequency list is L2. We're going to go down and press calculate. Now, for those of you that are using the Ti-83 calculator, or if you have an older display Ti-84 that has not been updated, your calculator might be displaying this as one var stats with a little box blinking. If that's the case, then you need to type in second and the number 1. That'll bring up L1. Comma, second, and the number 2, and that'll bring up L2. Now, if you watch my videos quickly here, it's going to show up for half of a second, and then it's going to show me the results. See, there it is, and there it goes. All right, so the mean is 2.32. Again, this mean is a theoretical probability. It is saying that if we were to look at the patients in this hospital for many, 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 many patients over many, 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 many weeks and many, 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 many 12-hour shifts, and average the number of times the patients will ring the call bell, the average of all of those would be 2.32. All right, we've got one more example here. It says, suppose you play a game with a biased coin. You play each game by tossing the coin once. All right, what does that mean? Well, a biased coin just means that it's unfair, meaning that it's going to land on one side more than the other. We're going to play the game by tossing a coin once. All right. What are we talking about? Well, the probability of landing heads is 2/3. So that's where the unfair or biased outcome is going to be. The probability of landing heads is 2/3. If you toss a head, you pay $6. Well, if I have to pay $6, that's me losing. If you toss a tail, you win $10. Ooh, I like to win. If you played this game many, many times, will you come out ahead? Well, if I play this game once, I have a 2/3 chance of losing and a 1/3 chance of winning. But if I play this game dozens of times, I'm going to win a couple of them. I'm probably going to lose a bunch more. But do I win more than I lose? That's the question. In order to make this a discrete random variable or a discrete probability distribution, we need to identify what that variable is. What is the random variable? Well, if I toss a coin, I have two outcomes, right? We're tossing a coin once. If I toss a coin once, I have two outcomes. One outcome is head and one outcome is tail. However, the discrete portion of this is the value, the number that's assigned. So in this case, we're going to look at the money value. The money value of the toss. I can win $10 or I could lose $6. Since I'm losing, I'm going to put -6 in there. All right. Now, the probability of winning, well, I win if I get a tail, but it says the probability of heads is 2/3. Okay, so the probability of losing is 2/3. The complement of heads would be tails, so the complement of 2/3 would be 1/3. And now I have my probability distribution. All right, so part 2 says complete the probability distribution. We've done that. Part 3, what is the expected value, mu, and do we come out ahead? Well, we can do this in two different ways. The first way is to grab the calculator, stat, enter, up, clear, down, over, up, clear, down. I'm going to put $10 for L1, and then I'm going to use the negative button. Make sure you use the negative button for 6, not subtraction. You'll get an error message if you use the subtraction button. The probability of winning is 1/3, so 1 divided by 3, and the probability of losing is 2/3, so 2 divided by 3. From here, we're going to press stat, go to calc, 1var stats. Same thing we've been doing for the last couple of examples, and we will get that mu is -0.66 repeated, or -67 cents. So do I come out ahead? No, I'm going to lose. In the long term of this situation, I'm going to lose money the more bets I make. Now, one other thing that we need to talk about, which we've talked about, again, just really quickly, this is theoretical, this -67 cents. I cannot toss a coin once with this scenario and get 67 cents. I can win $10 or I could lose $6 if I play twice. I can win $20. I could lose $12. Or if I win one and lose one, I can win $4. So that's where this idea of this -60 cents is coming in. If I play this game repeatedly, I'm going to eventually win a bunch, lose a bunch, and if I add them all up and divide, I will lose 67 cents per game. All right, one other thing that we need to talk about is how we can do this without a calculator. With something as simple as this quick calculation, I probably wouldn't even use a calculator for this. I would just add a third column, call that third column x times p of x, and then we could just multiply the $10 times 1/3 and the -6 times 2/3. And if I were to add these up, well, this would be 10 over 3, skip that step. And this would be -12 over 3, again, just top times top, bottom times bottom. If I find the sum of x times p of x, I will get -2/3. Well, -2/3 is just -0.67. So it's probably a little bit faster for some of these to just skip the calculator altogether. One last topic that we should cover here is that the sum of the probabilities must always add up to 1. The sum of p of x should be 1. So in this case, 1/3 plus 2/3 is 1. Did not show this with the previous one, but if we add up all of these probabilities, the sum of the probabilities for a probability distribution should always be 1. Let's just check that. So 4 plus 8 is 12, plus 16 is 28, plus 14 is 42, plus 6 is 48, plus 2 is 50. So I was just adding up the numerators because they all have a common denominator, 50 over 50. All right, so that is discrete probability distributions for the discrete random variable. And that's all we got.